Okay, so last week we pointed out that we solved the eigenequation for a linear operator T on n-dimensional vector space V. So this is the eigenequation. Okay. We select a basis B for the vector space V, and we consider the matrix representation. Okay, we call A related to the basis as follows, because we have so that the matrix representation actually satisfies this. Okay, and then it is. Alright, so this is the function value at x relative to the basis. So it's column vector in Rn. Okay. So this is the n times 1, this is n times n, and this is n times 1. Okay, so this is column vector AR, n, and this is a matrix, n by n matrix. So now with that, then by taking B coordinate, on both sides of the eigenequation. Right? So we have, so now here back B equal to come back B. Right? But we know taking the B coordinate actually it's an isomorphism, so it's projective linear transformation. And then, so we have that this is lambda is linear in particular. We have this one, and now we plug in this. We have P. i.e. we have A, B equal to lambda, okay, which is called the eigenequation for the matrix. Okay. So that we have a matrix, unknown column vector in Rn. This is a scalar, unknown scalar again, and the unknown. Okay, so now any scalar lambda in our scale field, so F is either R or C. Any scale lambda, and the vector I think okay, because well, this x is different from that x, but maybe it's better to use v here as a generic vector in the vector space V. So right? It's better for my presentation. If you don't mind, you don't change that. That's fine. Okay. If you know this x here is different from x here. All right. So x here I will denote it as a column vector. Okay. Satisfying ax equal to lambda x. Called an eigenvalue of A and an eigenvector of A associated with the eigenvalue number. Okay. All right. So we use the metric representation A of T directed to the selected basis B, and to form this eigenequation. So any solution, I mean any scalar lambda in our specific scalar field. And any column vector satisfying this eigenequation will be called the scalar lambda an eigenvalue, right, and also an eigenvector, right, associated with eigenvalue number. Any questions? Yeah. So what? Actually, so once. Let me finish that. Once an eigenvalue and associated eigenvector of equal to R1. Then we have that T then lambda and 3 equal to an eigenvalue and associated eigenvector. Okay. Then the lambda and the vector will be eigenvalue and eigenvalue and of course the eigenvector of T. So we can go back and find. So the eigenvalue will be an eigenvector. But there are questions. So the remark here. Alright? But there is a question. Well, lambda is different for different bases. Because that we find an eigenvalue lambda and then associated eigenvector by using matrix representation. But we know matrix representation A depends on the basis we choose. Right? Depend on the basis we choose. So the question is that if we use different bases, so we have different matrix representation. Well, the eigenvalue of 10 will be different for different chosen bases. So we will answer this question. Okay? We answer this question. Alright, so the basic result would be the first theorem, before 1.1. A scalar lambda is an eigenvalue of n times n matrix A if and only if determinant of A minus lambda equal to 0. Right? Okay? So now lambda is an eigenvalue of A if and only if there exists a non-zero vector x in Fn. Fn is either Rn or Cn. Okay. Such that Ax equal to lambda x. Okay, so by our definition, I forget to specify here. Because eigenvector should be non-zero. Otherwise, the zero vector always satisfies any eigenequation, no matter what is lambda. So it's so trivial that. So any eigenvector has to be non-zero. Okay. Alright, so lambda is an eigenvalue of A, even only if there exists a non-zero vector, a column vector, right? Satisfy this eigenequation. Okay. Alright, so this is given only if A minus lambda x equal to 0 for some non-zero vector x in Fn. Okay, so that means the kernel of A minus lambda is not equal to the trivial set. Okay? And if only if the determinant of A minus lambda is equal to 0. Okay, we know that in chapter 4. Okay. So this theorem is very useful because to identify whether a scalar is an eigenvalue of a matrix, we don't need to consider eigenvector. Alright, because we just try to solve this equation. Because this equation involves only the unknown scalar lambda. Because A is given, right? I identity is also given. And we know how to compute the determinant from chapter 4. So, and this is basically, I will show that this is a polynomial equation. Okay. So, okay. All right. So now, let A and B be two matrix representation of a linear operator representation. The linear operator P on an n-dimensional vector space V relative to basis B and C. Oh, okay, BB. So maybe I will change. Okay, D. Alright, so A and D be two matrix representations. Okay. For and E, A is P, and D is P. Okay? Okay, now my theorem. Let me see. Matrix representations are similar to each other, right? And let me recall the yeah, 5.3.5. A similar to D. So we know for different bases, relative to different bases, these two matrix representations are similar to each other. Okay? I there exists an invertible n times a matrix P such that A is equal to P D P. Right. So now the determinant. So now lambda is an eigenvalue of A. If and only if determinant of A minus lambda I n equal to 0. Okay? By theorem. Okay, we just prove it. Now, and then because A is equal to P inverse, so we have P inverse minus lambda. And what is identity? Identity can be written as P inverse equal to 0. Okay? Any problem with this economic condition? And then we have determinant P minus lambda I and P inverse equal to 0. So the difference between product of three matrices, and by the product formula for determinant function, so we know that this is determinant P, determinants of P minus lambda I n times n, and determinants of P inverse equal to 0 times the product formula for determinants. Okay, and then because P is invertible, so the determinant of P is non-zero. Okay, so now we can cancel them. So we have determinant of P minus lambda equal to 0 since non-zero. Okay. Okay, and again, by theorem, 6.1.1, lambda is an eigenvalue of P. So, when lambda is an eigenvalue of A, then lambda is also an eigenvalue of P. So that means that if we use different metric representations, the eigenvalue computed will offset no matter which metric representation is used. So we solve our problem, right? Eigenvalue, that's fine. Any metric representation will give us the same eigenvalue. Okay? Any questions? All right, so now since determinant of P minus lambda I is independent of. So actually the calculation of determinants is independent of the basis P selected. This determinant is also denoted as determinant of P minus lambda. Okay? And here, this identity is the identity linear operator, not the identity matrix. Okay? In chapter 4, we define determinants only for matrices. Alright? Remember, we haven't yet defined determinant for any linear operator. No, haven't yet. But in this context, that because the matrix representation, so maybe exercise for you. Exercise for you. So let T be linear operator on an n-dimensional vector space. Then determinant of P E equal to determinant of the term is independent of the basis be chosen for width. Okay? So please prove that. Please show that. Alright, so please ask you to do, please show that. The determinants of measure representation. Right? Because given you choose arbitrary basis B for vector space V, you get measure representation. So you can compute determinants, of course. You compute determinant. But I want you to show that this determinant value will be independent of the basis. Since that if you use different bases, and then you compute the determinants of the measure representation for that basis, the value will be the same, will not change at all. Okay, so you have to show that. Right? So in this case, let's we define the determinant of a linear operator be on an n-dimensional vector space. Will be the determinant of P is defined to be the determinant of P, where P is an arbitrary basis chosen basis for V. So this definition will be legitimate, means that no ambiguity. Because in this definition, I give you how to compute the determinant of P, give you the way to compute it. And also, I ask you to prove that this value is independent of P. Okay? And the technique you need to use is here. Okay, so this one should be becomes to a special case of this exercise. Okay. So later on, when we refer to determinants of a linear operator on a finite dimensional vector space, you know the meaning. Okay, let's take an example. One, suppose A right? So a metric representation of a linear operator, so where B is a basis for a two-dimensional vector space E over F. Right? So determinant of P minus lambda I equal to the determinant of the A minus lambda I 2 by 2. Okay? And now when we find that this is determinant of A is 2 minus lambda 1 and 4 and minus 1 minus lambda. Okay, so that this is determinant. And we know how to compute the determinant. So this is 2 minus lambda, minus 1 minus lambda, minus 4 times 1. Okay. Right, so this is lambda square, minus lambda minus 6. So this is lambda minus 3, lambda plus 2. Okay. So which is a polynomial of degree 2, lambda, and we have factorized it, right? Factorize this polynomial already. So that we solve when we solve this equation, the determinant of t minus lambda I, we find that lambda is equal to 3 or minus 2. Alright, so minus 2. That P has 2 eigenvalues. Three and minus 2. Now to find the eigenvector, I put x. Maybe we have more than one eigenvectors, right? We don't know. So to find eigenvectors associated with the eigenvalue lambda equal to 3. We consider the eigen equation with lambda equal to 3. So we have to find the eigenvectors for each eigenvalue. Okay. So now we have to solve PV equal to 3 with. Okay. So we have now solved. If we know 3 is an eigenvalue already. Okay. And now when we take so now this is going to okay, and so we have the A and the x equal to 3x. Okay, because x unknown, v unknown, so x is also unknown, right? So we want to find x satisfies 1. And so basically, right? So we will solve homogeneous system linear equations. So what is that? This is minus 1, 1, 4, 4. right? So the automatic matrix so by row operations we have one, so the pivot here. Okay, and so this is implies that we have 1 minus 1 0 0 and alpha beta equal to 0 0. So that this says that kernel of A minus 3 3R is equal to by 2 alpha alpha so it's alpha alpha like that, and so it's one dimensional. So any non-zero vector x in the kernel of A minus 3I 2 by 2 is the B coordinate. Right? So any non-zero vector is the B coordinate of an eigenvector V of T associated with eigenvalue lambda equal to 3. So actually the kernel of the matrix representation A minus 3 times the linear matrix actually consists of all vectors. There are any non-zero vector in the kernel is an eigenvector of A of the matrix A, corresponding to eigenvalue 3. And then it's the B coordinate of an eigenvector of T associated with eigenvalue number 3. Okay. So we solve the eigen equation for eigenvalue number. Now so if B consists of V1 and V2, okay, then with x equal to 1 1, which is B with x in kernel of A minus 3I, we have the V equal to V1 1 times 1 plus 1 times V2, which is V1 plus V2. So V equal to is an eigenvalue, an eigenvector. It's an eigenvector of T associated with eigenvalue. So specifically, if you take 1 1 in the kernel here, because it's non-zero, so we can form a non-zero vector. So this non-zero vector in V is an eigenvector of T associated with eigenvalue number 2. So this demonstrates how we solve the eigen equation. Okay, so similarly, right? For eigenvalue number equal to -2, we have the kernel of A minus 2 I becomes 2. Okay, this kernel is equal to actually alpha 1 minus 4 given alpha r. So you can solve the same scenario. Then you can solve this kernel for the eigenvalue number equal to number -2. Okay, so that any non-zero vector in this kernel is the p coordinate of eigenvector of t associated with eigenvalue -2. Okay, so that's in particular 1 minus 4 is the p coordinate of an eigenvector v equal to 1 v1 plus minus 4. So it's minus 4 v2, which is v1 minus v4 v2. So that the big of an eigenvector of P associated with eigenvalue number equal to -2. Okay? So now we summarize. Now, for the matrix representation A, you know that A 1 1. Okay, we get 3 1 1. And the A minus 4, we get -2 -4. So the vector and the scalar 3 satisfy this eigen equation for matrix A, and also the vector 1 minus 4 and scalar -2 satisfy the eigen equation. So we have that. Now it can be seen that C, if we use 1 1 and the 1 minus 4, you see that it's a basis for the R2. Okay. Right, so and this basis corresponds to a basis. Okay, so we call this C tilde. Okay, to a basis C, which is V1 plus V2. V1 minus 4 V2. Okay? For V. Okay? So originally, So the original basis we chose for B is V1, V2. Okay? And now this basis corresponding to, because they are B coordinate, all right, of vector B, so that the corresponding vector C V1 plus V, V1 plus V2, V1 minus 4 V2 is the basis for B. Okay, and then T V1 plus V2 equal to 3, V1 plus V2, and T V1 minus 4 V2 equal to minus 2, V1 minus 4 V2. They are corresponding to these two eigenequations. Right? Thus, the metric equation relative to C, the metric representation of T relative to C with this basis okay? So what is that? It's V1 plus V2 take V1 minus 4 V2 C. Okay? This is the metric representation we have, the column vector. So we select the oh sorry too fast. V1 plus V2 C B V1 4 V2 C. So the image of the first basis vector, take the C coordinate again, and we take the transformation of the second vector in the basis C, and then we take the C coordinate of this image. Now, because here, this is 3 plus, and so we can express the image as a linear combination of this basis vector. So this is 0, okay, and here is like 0, minus 2, okay. So the metric representation, this one is 3, 0, and this one is 0 minus 2. So the metric representation is come to diagonal metric. So compare with the original matrix A, which is not diagonal. Okay. Then we now have a diagonal, so which is diagonal. All right. So the summary is that okay, and so we conclude that we can find diagonal matrix representation. Three zero zero two P things we can construct a basis C for V with U equal to V1, V2 and W equal to V1 minus 4 V2 where V1 is the original chosen basis for V. So, since we can construct a basis C for V and consisting of eigenvectors of so the reason is that we can construct basis by using eigenvectors of because for eigenvectors we have simpler images so that when we expand them we will have a diagonal vector representation. Alright, so this is a very nice example, right? For this example, we find eigenvalues, and for each eigenvalue, we find eigenvectors. And we are very lucky that we can find a basis for the vector space V, and the basis vectors are all eigenvectors. That's the point. And then we will wrap it to this basis. We call eigenbasis, okay? So later on we will say that this one is an eigenbasis. V, right? So we have eigenbasis for V. Under P. So we've okay. Now let's take a second example. This time A is 2102. Okay. All right, so now we solve A minus lambda equal to 0. Okay, so we want to solve it, and so we want to determine of 2 minus lambda 1 0 2 minus lambda. Okay, so we find that we have lambda minus 2 squared is 0, and it's easy, so lambda is 0. Oh, it's 2. 2. So we have one eigenvalue with multiplicity 2, right? So that that we have an eigenvalue lambda equal to 2 with algebraic multiplicity, algebraic multiplicity 2 for x. Okay, for A, and then, of course, for T. Okay, because that if we use different metric representation, right? If we use different representation, then we'll get the same eigenvalue too, and with the same algebraic multiplicity. Why we call this algebraic multiplicity? Because we solve the algebraic equation here. Right, and later on we will have another multiplicity for an eigenvalue later. And that would be an important distinguish between these two kinds of multiplicities. Okay, but here we have this way. Okay? So that not like the previous example. In the previous example, we have two distinct eigenvalues, 3 and minus 2, right? But in this example, we have only one eigenvalue, but with multiplicity. Okay, so the kernel of A minus 2I, right, is the kernel of, so the kernel, what is that? It's 0, 1, 0, 0. It's the kernel here. So what is the kernel? To be 1, 0. Because it says that the second component should be 0, but the first component can be arbitrary, right? So we have that the kernel is here. Okay. And the dimension of the kernel of A minus 2, right, is 1. Okay. So that which is less than 2. This is the only way we can find eigenvectors, because that we have only one eigenvalue, number equal to 2, and the eigenvector corresponding to eigenvalue 2 are just all non-zero vectors in here, in this kernel. But we cannot find two linearly independent eigenvectors associated with the eigenvalue not equal to 2. Because this kernel has dimension 1 only. Alright, so that's P has no diagonal matrix representation. So that's we cannot construct a basis C or V consisting of eigenvectors. Right? So impossible, you can't. So, right? So that's P no diagonal matrix representation. So no, there's no matrix representation for such a linear operator. No, you can't find that. Any questions? Third example, A, it's a matrix representation. Okay, so the matrix representation relative to a basis is 1, 2, minus 1 here. And then the determinant, we try to find 2, which is equal to determinant of 1 minus lambda, minus 1 minus lambda, 2 minus 1. Okay. And this is number square plus 1. Wow. Which has no real root. Right? No real root. So we don't have any real eigenvalue. So if our scalar field is real numbers, so if the scalar field is R, then we will, because the matrix here, the representation is real entries, so this is a real matrix. So if the scale field is R, then we will have no real eigenvalue. Wow, that's very serious. This is a very serious problem. We don't have any real eigenvalues. With no real eigenvalue, we cannot find any real eigenvectors, right? So, of course, there is no hope to have a diagonal matrix representation. Right, so that is this situation. Yeah? Okay, so I think I stop here, and you can take a break time, we go to the restaurant, and then we will, after 5 minutes, we will take this examination. Okay.